In this video, I will be going over ERP waveform plots and topographical scout maps. This slideshow was created by Pursue and was modified for this presentation. During the slideshow component of the video, you should learn to appreciate why data visualization is important in research, recognize how specific parts of the ERP data are best communicated in different types of plots, and apply best practice guidelines to make effective figures for ERP waveform plots and scout maps. In the tutorials after the videos, I will teach you how to create figures of ERP waveform plots using ERP data, as well as for topographical scout maps. Before event-related potentials can be analyzed, there are a few variables that must be known. One of which is amplitude, which is the distance of the peak of an event-related potential to the baseline of the graph. For positive ERP components, the amplitude will typically be positive. For negative ERP components, it will typically be negative. Another variable is latency, which is the time interval between the onset of a stimulus and the peak of an ERP component. One more important variable is scalp distributions of electrical potentials. Electrodes across the scalp will have varying voltages, and topographical maps, like the one on the slide, will show how these distributions at only one point in time. In these maps, warmer colors are often used for positive charges, while cooler colors are used for negative charges. You should remember that each condition in an experiment is going to affect an ERP waveform in different ways. The waveform on the right side of the slide demonstrates the ERP waves resulting from the three conditions. One way these ERPs can differ is amplitude, and a visual example of this can be seen in the figure. When analyzing the N170 component, the pink condition has a noticeably more negative amplitude than the green condition. It's possible that such amplitude differences indicate that the amount of processing used for a cognitive task varied across conditions. However, amplitudes alone cannot indicate whether this experimental condition used the same cognitive processes. In general, a psychological interpretation of amplitude differences requires a good understanding of what you are studying. Another way ERP waveforms can differ is latency. Differences in latency could show that a cognitive process is happening at a faster or slower rate in one condition when compared to another. One example of a latency difference is seen in the figure. The ERP for the pink condition visually peaks earlier than the ERP for the green condition. This means that processing in the pink condition is faster than in the green condition. While ERP waveform plots are needed to see differences in latency and amplitude, scout maps are needed to see differences in topographical data. The scout maps on the slides show the distribution of the electrical activity for the N170 ERP for words compared to faces. What these scout maps reveal is that word processing causes the N170 to be lateralized to the left hemisphere, while facial processing causes the N170 to be lateralized to the right. These scout maps are good at showing that different cognitive processes are being utilized when processing either words or faces. It is important to analyze all three of these variables when doing research on any ERPs. So one good reason why you should become familiar with ERP waveforms and scout maps is because understanding visualized data is an essential skill in any scientific research. Data visualization entails things such as graphs, tables, figures, and charts. It is an efficient way to share data, allowing you to tell your research story. When researching ERPs, a good question to ask yourself is, did our research questions emphasize timing, strength of response, or distribution of response? To help answer research questions, you should ask yourself, how do we create graphs to communicate answers to our hypotheses? When thinking about creating visualized ERP data, some questions you might want to ask yourself are, how do you plot your ERP data so that you can best communicate the results? Or how can EEG/ERP plots show how experimental manipulations affect neural responses over time and across the scalp? Data visualization is also a good way to show the validity of your data. In other words, this can show if your data is of a good quality. Of course, figures can answer whether or not the EEG data was processed properly. Things in good quality data are a flat baseline, amplitudes within the ERP voltage ranges, ERPs in the expected electrodes, and distribution of electrical activity in the expected time frame and scalp region. It should be noted that figures also relate data back to any statistical findings. Say you're reading a research paper on the unknown study ERP, that's what's depicted on the figure in the slide. And in the results section, you read that there is a statistically significant difference between the amplitudes of ERPs between the two conditions, so phases and cars. The waveform plot shows that result, and this figure is a perfect way to see how different the amplitudes are. There are many utilities that these figures provide, and understanding the results of an experiment is one of them. Without a doubt, you'll be interested in some variables in data more than others. Your results can convey information about things about ERPs, such as timing of the response, amplitude of the response, location of the ERP, topographical scalp distribution, and more. Remember that there is not one single figure that can show everything in your study. There are different figures that serve different purposes. The three figures on this slide demonstrate this. I will be going over single electrode waveforms and topographical scout maps. Whole head waveform plots, so the one in the middle, just show the waveforms for every electrode. I will not be going into too much depth for this one since Dr. Lyons rarely publishes them, if he even ever published one at all. The waveform plots that you are all familiar with best emphasize the timing and strength of the neural responses associated with cognitive processing. Like any other figure, waveform plots can be used to answer specific questions. So for instance, the question on the slide, is early perceptual coding for faces different from other objects, is answered by the waveform plot on the slide. You can see here that the N170 ERP in the faces condition peaks earlier than in the cars condition. This shows that there is a faster processing in the faces condition, and because the N170 peak is negative, it is also evident that there is a stronger neural response in the faces condition. Topographic scalp maps emphasize the spatial distribution of a neural response. These show the electrical distribution of the scalp at single points of time or at a time interval. You may ask yourself, what are some EG/ERP questions that topographical scalp maps answer? I personally went over this figure before, but one question these scalp maps answer is if face processing happens more in the right hemisphere than left hemisphere. With all this knowledge about these figures, you might be wondering if you should be using waveform or scalp maps to emphasize important comparisons for your study. You will most likely end up using both, but to address specific questions, you still need to decide which one is best. If you are hypothesizing that your experimental manipulation will affect the strength and timing of the cognitive process, then you'll want to use a waveform plot. On the other hand, if you are hypothesizing that your manipulation will affect the spatial distribution of response, you will want to use a topographic scalp map. That was an overview of the figures used in ERP research. Now I'll be going over the specifics for waveform plots. For any ERP study, you should expect that the data in the results is grand average data. Grand average data is the average data of all the study's participants. You can plot the grand average data for one electrode. When making that waveform plot, you should only use an electrode where the effect clearly happens at that location. So the figure on the slide is a perfect example of that. Single electrode waveform plots will show timing and amplitude differences of an ERP effect. These waveform plots will show the changes in voltage as a function of time. If you want to get more elaborate, these waveform plots visually compare latency and amplitude peaks across experimental conditions. Now, waveform plot is only good for a single electrode. They will not yield any information about scalp distribution. To create one of these waveform figures, you need to know all of the important parts that make it up. For any graph, you must always remember to label your x-axis and y-axis. If you do not label your axes, then the layman will be confused about what the graph's variables are. You need to also label which electrode site the waveform plot is for. For example, this waveform plot is for the CZ electrode. The x-axis for ERP waveform plots is time in milliseconds. The x-axis values should be spaced out enough to show the full component. Time zero is simply 0 milliseconds on the graph. This is when your event starts. Anything before time zero is before the event, and anything after is after the event. The time ticks are present on the x-axis to show where each point in time is. This allows you to know the time course of the ERP waveforms. The y-axis is in microvolts. The y-axis measures the range waves. Again, the numbers should be large enough so you can easily see the component's peaks. The x-axis is located where y equals 0 microvolts. This is also where the baseline is. Furthermore, you need to show if positive voltages are above or below the x-axis. Negative signs must be used to represent the negative voltages on the graph. Plus signs can be used to represent the positive voltages, but plus signs are not exactly required. The voltages should also have equally spaced tick marks on the graph so you know exactly where they are. You need to choose an appropriate range of numbers for the y-axis too. Your goal here is to make it so that the ERP waveforms can fit onto the graph. If the waveforms are too big or too small, then you need to change your y-axis range. The waveforms for each condition will need to be able to be visually differentiable. Colors are a good way to differentiate conditions. You can also use different line types. Examples of different line types are sols and dashes. Of course, you need people to know what they're looking at. Your figure will need a legend that matches the different waveforms with their conditions. Now, I will be going over a few errors that you would want to avoid when creating waveform plots. In the first example, you are unable to see the top of the peak for the black waveform. This is because the y-axis is too small. Always make sure that the y-axis is big enough to see the full amplitude of the component. In the second example, you cannot see what is happening before the event. Furthermore, there's no legend uh, for the conditions. Your figures will always need a legend if there are multiple conditions, and you should also show what is happening before the event. In the third example, you cannot see the entirety of the waveforms because the x-axis is too short. Again, make sure that your x-axis is long enough when making figures because you do not want to leave out any important data. In general, it is unlikely that the x-axis or y-axis generated in ERPLab will be too short, but you should always be on the lookout for any of the errors on this slide. Here's a summary slide. I have went over these points a couple of times, but feel free to read these at your own leisure. I will now be going over the specifics of topographical scout maps, which are another important tool in ERP research. One important thing to remember is that topographical maps show the variations in voltage from channels across the entirety of the head. From that data, you can determine if ERP effects are broadly or narrowly distributed across the head. It can be seen from the pictures on the slide show how topographic scout maps come to be. First, the electrodes record electrical activity. At a certain point in time, the unsmooth voltage is recorded by each electrode. The voltage of each electrode is assigned a color represented on the amplitude legend in the middle figure. Finally, the voltages are smoothed out, forming the final product seen in the rightmost image. A good skill is being able to read scout maps for spatial information related to specific effects with scout topographies. So say you are investigating the N400 ERP component. As you can tell by the name, it creates a negative peak. The N400 produces posterior old/new effects. This would mean that you would need to focus on the parietal electrodes to see its negative effects. One thing that should be emphasized is that you can compare scalp maps belonging to different conditions to see the ERP effects. One example you can use is this figure. All the conditions in this figure are word primes used in a Linus 2023 study. It is evident that the matched prime condition produced more positive effects than the unrelated prime. In addition to conditions, remember you can also plot scalp maps belonging to certain time intervals or just single points in time. However, you must remember that one scalp map cannot show how an ERP appears and becomes altered across time. You would need scalp maps from different time intervals to help you see that. Here is some review on the color coding of scalp maps. One way to think of the color bar is as a scale for polarity and a scale of amplitude voltage. Anyone has the freedom to choose the color gradient that they will be using for the scalp maps. However, generally, hot colors represent positive deflections, while cold colors represent negative deflections. The locations of electrodes are always going to be represented by black dots. In this figure's case, the black dots are not so broad. Not all scout maps and research articles have these black dots, but in my opinion, they are a good reference to have. Uh, Two other key features of scout maps are the time and condition. You won't know the significance of the scout map without these things. Here's just a pretty good example of what an aesthetic figure of a scout map by itself looks like. Pause and take note if you need to. In literature, you will often see figures combining single electrode waveform plots with topographical maps at a certain time interval. Of course, the ERPs on the waveform plots are grand average. In this case, topographic maps from 300 to 500 milliseconds are being shown next to waveform plots. One reason why waveform plots and scout maps might be placed side by side is to communicate how the scout maps relate to the waveform graphs. You can see this relation when looking at the PZ waveform plot. The PZ electrode is, of course, located at the parietal area of the scout. You can see in the plot that the uppercase waveform is visibly higher in amplitude than the unprimed waveform from 300 to 500 milliseconds. Looking back at the scout maps, you can see that the parietal area of the uppercase scout map is more positive than the parietal area of the unprimed scout map. When making these figures, you're striving to be consistent, so make sure that all of the scout maps are the same color gradient and that all of the waveform plots have wide x-axes of the same size. This way, it is easier to see the similarities like the one I mentioned. This is another special figure that you might see. I'll refer to it as a time series because it shows scout maps for certain conditions at different time intervals. In this figure, each row is represented by an experimental condition. The scout maps from each row are subtracted by the topographic data from the control condition. In this case, the control condition is the unprimed condition. Anyways, you can see in this figure that the effect can be seen in the 300 to 500 milliseconds interval. Anything before or after that does not reveal anything significant between the primes. Like what I showed for the waveform plots, here are some errors you might encounter when seeing scout maps. The first error has a lack of information, so you're getting nothing out of seeing this figure. The second error also suffers from a severe lack of information. The lack of a voltage scale makes these scout maps meaningless. The third error is an improvement over the previous figures, but there's no condition labels for either the waveforms or the scout maps. You cannot make any meaningful comparisons without these labels. Here are the take-home points for scout maps. I will now be getting into the tutorial. I will be starting off with how to make waveform plots first. Your first step is to open up ERPLab, click on the ERPLab tab, go down to load existing ERP sets. Um, I'm not doing this tutorial on a lab computer, so I already loaded an ERP set. On the lab computer, just locate your study's ERP set and select it. And after that's done, you're going to go to plot ERP waveforms. Okay. In this menu, you're going to deselect this first, then deselect this because you don't want all the bins. Now you can hit browse. Uh, for this step, you need to choose the bins for the conditions that you are investigating in your study. I am personally interested in bins 31 through 33. You can change the time range if you want. I am going to. So I'm going to make it negative 150 milliseconds to 800 milliseconds. Then after you do that, you deselect this. And now you can plot the ERP. After that's done loading, now you're going to click on the electrode of your choice. So for me, that is FZ. After this big view of your waveform shows up, now you're going to hit Property Inspector. And after that's loaded, you can now move your electrode site to the x-axis. And I'll be putting this here. And now I'm going to move the figure legend to below the graph and make that horizontal. Okay. So once that's done, you're going to save this as a JPEG. All right. I already have that as a JPEG. It's automatically a figure, so you'll need to change it here. I'm going to rename this to data visualization, form plot, click save. And now I open an image editor. I'm personally going to use Google Slides for convenience. You have to do this because you still have to add units to your axes. I decided to do this part off screen because image editor is different functionality. But now you can see that I have labeled both the y-axis and the x-axis. The font that I'm using is Arial. I also decided to tweak this figure too in another way. So I actually just put a text box here because I felt that the FZ was too small. But overall, now this figure is complete. There are also more features that can help you when creating ERP waveform plots. You can include time ticks relevant to your experiment by selecting time ticks and manually typing them out. You can choose which channels you want to plot so that ERPLab doesn't load all the channels. If you do this, you should also change the number of rows and columns that each electrode will appear in. That way, the ERP waveforms will be sized properly in the window that appears. If you want to change the baseline of your study, you can change the baseline correction setting. For instance, I'll select custom. The ERP waveforms can also display the standard error of the mean uh, at each time point. You're able to multiply the standard error by like any integer here. And you also can change the transparency of the area that displays the standard error. So if you go like towards 0, then you get an area that's like more opaque. But if you go towards 1, you get an area that's more transparent. I personally prefer to use 0.9. The colors of each waveform can also be changed. So if I wanted to change the color of the third bin, then I can just select any of these colors. So here I'll just change to green. You can also change the line type of each waveform. So I can, that also like works similarly to like how you change the color. So I can just change it to like a dotted waveform. I'll just press OK. And now I'll plot to see what we get. So first go to ERPLab, go to plot ERP. This time you're going to go to plot ERP scout maps. Once the menu loads, choose bins to plot. So you're going to choose the bins that you want. I personally want bins 31 through 33. Then for value to plot, you're going to choose mean amplitude between two fixed latencies. Then now choose the latencies that you want. So for me, that's 300 to 500. And then next, go to color bar scale. And for that, I want custom. And I'm going to choose -4 microvolts to 4 microvolts. This step is done so that all three maps are on the same color bar scale. And after that, you're going to want to display color scale bar. And now you're going to choose a gradient. This step is optional, but you can choose any gradient you want. I personally like jet. So once that's done, go to options, select bin description, press OK, and now you're ready to plot. All right, so full screen that. Okay, so go to property inspector since you want to move this. Okay, now that property inspector is loaded, you're going to move the color bar scale to over here. So just try to center it. All right, this is a relatively good location. So now I want to switch to axes, and I'll show you what I mean. So go to position, and for axis location, select in, and now you can see the axis is in instead of out. So I don't need this anymore. So what we now have is 3 scout maps, all matched to the same color bar scale. They all have bin descriptions, which I'm going to replace with condition labels, and you can do that with a image editor. Of course, you're going to want to save this image as a JPEG. So first you're going to go to File, Save As. It's the same as for the waveform plots, but this is still good to show. So I'm going to tell this data visualization, scout maps, and save. I've edited out the bin descriptions and labeled each scout map with a condition, and I've also added a time interval. So now you can see that this is a complete scout map figure.